Um, One thing I did here is when I cut the original leads, I took loads of pictures, copious amounts of pictures, but also when I cut the lead, I didn't cut it all the way to the base. I left some blue sticking out, so I knew that blue one matches with that. And this red one matches with this one right here. Okay, and the black is still attached up here. Okay, in this section what I wanted to do was show you why it's so important to replace these paper capacitors. Even if something hasn't been used for years, they can still go bad. I have a Solar CB60 capacitor checker and resistor checker. And basically how it works is you can read the capacitance by turning this knob here, read the capacitance while looking at the eye tube for maximum deflection, and I'll show you how that works. First of all, we'll start off with the electrolytics. There's 3 electrolytics in this radio. In this one they have 240s in here and 120 here. And we'll start with the one section of the 240s here. And basically you put it on a scale that you want to test. This will be 40 microfarads. So this red scale will read up to looks like 70 microfarads, but we want 40, so it should read around here. And we'll just hook up this to one section. You just put it on the scale, hook up your leads, and you turn this and look at the deflection. See, it's closed. See it open it up there? I hope you can see that. And then you read maximum deflection and you read the capacitance. And it says just about 40. Okay, so that looks good. Now you rotate this dial all the way to the right, okay, and then you check for leakage. And you set this for 0 volts. This will be 100, 200, 300, 400, 500 volts. Okay. If this light stays on for a long time, the capacitor is leaking. Now this is a 150 working volt capacitor. So the maximum I want to put is 100. If I put it on 200, it'll overstress it. But as you can see, it charges up and then the light dulls down when it goes down to 0. It tests pretty good. Okay, it's definitely not real bad. I would not use it, but I just want to show you. Okay, we'll put it back on C1. This is another 40 microfarad, so we should see it open up, and we do. Maximum deflection, about the same place, 40 microfarads. Rotate this all the way to the right, put this on 0, and I can go up to 100 but no higher for this capacitor. Okay, that one tests okay. Alright, let's test the third electrolytic. You always want to make sure that this meter is at 0 volts, because if I do this and it's not at 0 volts, I'm zapped. You don't want to do that. Okay, go back to the C1 scale. Now this is 20 microfarads. So, 20 microfarads is around here. This is closed. Now we look for maximum deflection. And, wait a minute, there is no deflection. And the deflection happens here, and it reads open. So this capacitor is open. Internally, it's not connected. So this capacitor is definitely bad. It's essentially not even having one in there. So as you can see, these things do go bad. I did test a couple of others, and they did test pretty good, but I bet there's at least a couple more in here that are bad. It's just better to replace every single capacitor in the unit, because even if it tests okay now, these things are still 60 years old. So 5, 10 years down the road, you know, it would be bad news if one of them shorted out. Could kill a tube, cause a fire, who knows what could happen. So anyway, so that's it on that, and I just wanted to show you that the capacitors do go bad. So I will be replacing all these capacitors. Well, I think I'll start by removing the largest electrolytic here. I already clipped out the blue and red leads here, and I left enough on the pins to tell where the blue and the red go. And I'll do the same thing for this black common negative over here. Snip that out. Okay. See a little bit there. Alright, that takes care of this. This is the dual section 40 microfarads, which I initially will replace with a 40, 47, and a 22. And like I explained earlier, I'll listen for hum after I get it all together. And if it sounds good, then I'll leave it. And if it doesn't, then I'll add the 40. I might end up adding the 47. I might end up putting the 47, two 47s in there. Anyways, because what I could do, it will really reduce the hum, but we have to worry about surge current through the rectifier again. And to eliminate that, these sets anyways were made to run at a lower voltage than the normal house voltage. Now, the normal house voltage is somewhere around 122 volts nowadays. And back then it was 110, 115 volts. And so that's a few volts less. Now what I can do, there's a thing called a CL90 thermistor. What that has is when it's cold, it has high resistance. Okay? And because it has high resistance, when the tubes want to draw a lot of current and the capacitors want to draw a big surge from the rectifier too, that limits that. And then as the thermistor heats up, it allows more current to go through because it lowers its resistance. So we can have the best of both worlds. We could have better filtering and very little surge, and actually a side effect of that too is it actually lowers the voltage. So it may run at, say, because I think the CL90 is, I think it's something like 190 ohms when it's running hot. So during the normal use of the radio, after it warms up, it acts like a 190 ohm resistor in series with the circuit. So it may overall bring the voltage down from 122 to around 115, say. And that's what it was ideally constructed for anyway. So the only thing about a CL90 is it gets fairly hot. So we need room in here to put it so it's not too near anything. I think there'll be loads of room in here once we get rid of this big filter capacitor and this filter capacitor and all these other paper ones. The newer components are real small, you'll see that. And then all of a sudden it'll look like there's a lot more room in there. So I probably would go that route. And it will make the tubes run last longer too, because when the filaments are cold in the tubes, without that thermistor, they're going to want to brighten really bright real fast, because the internal resistance of the filaments is low, and so it really wants to soak in the current, and then you'll see this big glow, and then as the resistance builds up it gets dimmer and dimmer and dimmer. Well, you can eliminate all that with that CL90 thermistor. So that might be the best of all possible worlds. So I won't know yet until I get it all going, but that's probably the route I'm going to end up taking after all is said and done. Alright, well that takes care of that. Let's also remove this capacitor electrolytic, which was a 20 microfarad at 150 working volts, which is this guy right here. plus side of the electrolytic goes to the 12SA7 pin. I changed the lighting in here so you can all see it better, but it's darker for me, but it should be less glaring for you. So it's hard for me to see the notches, but I feel it for the pen. So this is 1, 2, 3, 4, pin 4, the 12SA7. Let's see, 12SA7 pin 4. There we go, right there. That's the plus side. And the negative was just connected to chassis ground, which, as you can see this leg here, see all the wires soldered to here? That's because chassis ground and, common ground, this is common ground. It's not the same thing as chassis ground. This is chassis ground, this is common ground. So this terminal is the common ground for the circuit, but it's not tied directly to the chassis. Okay, it's a floating ground okay? And so that's why there's so many components soldered to here. There'll be other ones around here with a whole group of connections, and that will be the common ground, which is designated by this symbol. Okay, so anyways, in this case, because physically it's big, they put this part on this tube, which it goes to, and this part here on a different tube further away. That's a common ground. Okay, which happens to be pin 1, 2, 3, pin 3. All right. Well, I guess in this case, I might just leave it up like this and start replacing this guy and this guy here. As you can see here in the video, okay, this capacitor, which is, now I have to use my flashlight here, it's a 0.05 at 200 volts. Okay, and it goes from pin, it goes from that common ground to chassis ground. So here is an instance right here where there's a capacitor that goes from chassis ground to common ground, and it's 0.05. Let's see if we see one that does that.